Hello everyone, this is Dr. Ian. For today, we're going to be working on tangent lines in relation to circles. One of the reasons why sometimes math problems can be a little bit difficult to answer is because we are not familiar with the words that is being used in asking questions involving problems in mathematics, specifically in geometry. And that's what we're going to be working on today on circles, specifically on a special line called tangent line. And we know that we are familiar with the word tangent from our lesson on trigonometry, which we can also use in geometry as a descriptor of a line that is in relation to our circle. So what are tangent lines? So by definition, tangent line is a line in the plane of the circle that intersects at the circle in exactly one point. And how are we going to better understand this? But with a visual. So let's have a circle here and this line that we call as a tangent line. So according to the definition, the line should only intersect only one time on the circle, and that's what we're going to show. So let's say we have point B right here, and we're going to draw a line that will connect to the circle, specifically to point B only one time. Therefore, we're going to have a line that is touching our B, but not really crossing our circle. Otherwise, it will give you 2 points of intersection. So all tangent lines are lines that is just on top of the circle, and it needs to only touch our circle with only single point. So since in geometry, the notation for lines requires you 2 points. So let's say we have a point on our line, point A. So now we can denote our tangent line as tangent line BA. And in some cases, we know that our notation for any line segments or lines in geometry, if we have line BA, this is also the same if we write line segment AB. So it doesn't matter how you position your letters as long as you are including the letters that signifies or denotes our points in the plane, then this will be correct. So this is our tangent line BA or tangent line AB, which we can also call as ray AB, denoted by this particular symbol, or we can also write line segment AB like this one as a tangent line for this particular circle. So now that we know how tangent lines are illustrated, now let's talk about a special point in this particular tangent line, which is point B. Now, point B has a special term in geometry, and we call it the point of tangency. And the point of tangency, of course, is the single point on the circle that is intersecting our line and our circle. So again, it's important that we know these words that we use in some geometry problems that we will encounter in the future, and this will help us to be able to be more confident in working with problems in geometry if we know the terms, the symbols, and the notations that we are using in problems like what we're going to be working on in a little while. Now, the first theorem that we're going to be including in our lesson today would be the tangent radius theorem. And according to this theorem, if a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So what does it mean? So let's use our tangent line from our previous slide. And let's say that this particular circle has a center at O. And if we connect our center and any point on our circle with a tangent line, that tangent line will form a we will form a 90-degree angle, because in this case, line segment or line AC is tangent line to circle O. Therefore, line segment OB is perpendicular or forms a 90-degree angle with line AC. And this is how we illustrate it in our diagram and how we write it in symbol form. And in sentence form or in English form, we read this as line AC is perpendicular to line segment OB. So in this particular theorem, the tangent radius theorem, so let's say we have a circle O and we have a point, let's say point M right here. Knowing that we have a tangent line here and connect it with the radius of O to M, this particular line, even though it looks like as if it's not a 90-degree angle, but this is a 90-degree angle that will be formed by this particular circle. Ugly circle because I am not using a compass, but we are understanding that this is true because of our tangent radius theorem. So even if our line is not looking like perpendicular to this particular form, but because of the theorem, we know that this is true. So this is how we use or denote our tangent radius theorem, and we're going to be using that in this particular problem that we are going to answer using this theorem. Now, given that the radius, or given that we have a circle C and this particular diagram, and noticing that we have a right triangle, we'll be able to find the value of x, which is the radii of our circle, using the Pythagorean theorem, and of course, using our radius theorem from our previous slide in this particular geometry problem. So let's write out our Pythagorean theorem. So what is the Pythagorean theorem? We know that the Pythagorean theorem is hypotenuse squared equal to legs squared plus legs squared. And in this particular circle, we know that our hypotenuse, using the Pythagorean theorem to find the value of x, is the longest side of this right triangle, denoted by line segment AC. So line segment AC is our hypotenuse, and we're going to square it to start with our Pythagorean formula. Now, the other leg that we can use is leg BA or AB, and this will be our first leg, and we will add it to the other leg in this particular right triangle, which is line segment BC. So now that we have formulated our Pythagorean theorem in relation to our circle and triangle, all we need to do is to write out the values of each of these line segments. So for line segment AC, we know that AC is connected with line segment with 8 units and x. So what we can do is add these two values so we can form line segment AC. So AC is going to be an expression, and it will be x plus 8 units, and we're going to square it, and that will denote our line segment AC. And for line segment AB squared, it's going to be pretty straightforward because we know that it's just 12 units, and we're going to square it, add it to line segment BC, which happens to be x, and then we're going to square it. So now that we have our expression, we can simplify this using algebra, and we know that x plus 8 quantity squared can be expanded, and by multiplying x plus 8 times x plus 8, you can use FOIL method, or you can use this technique, x squared plus twice of 8 and 8 squared, and that will be our expansion, equal to 144 plus x squared. And from here, we'll be able to solve for the values of our x, or value of our x, by equating it to 0. So we are going to subtract 144 on this side and subtract x squared on both sides. So our new equation will therefore equal to 0 because this cancels out, and now we have x squared plus 16x plus 64 minus 144 minus x squared. You're not seeing the x squared, but you know that we have here the x squared, and by completing our, or combining like terms, we'll be able to simplify our expression and equate it to 0. And we're going to do it on this slide so that we'll be able to see it better. So now that we have established our Pythagorean theorem, we know that AC squared is x plus 8 squared. We know that AB squared is 12 squared. And we know that BC squared is x squared. We expanded x plus 8, which gave us x squared plus 16x plus 64 equal to 144 plus x squared. And by equating it to 0 and combining like terms, we'll have a quadratic equation that will look like this. So we cancel out the x squared, and now we have 16x equal to 80. And by dividing both sides by 16, we know that the value of our x is equal to 5. So that means the radii of our circle is 5 units long using the Pythagorean theorem, and of course, the theorem that we used from our slide a while ago. So this is how important theorems are, and of course, the use of your algebra skill to solve for some measurements like this one. Now, let's have the second theorem, which is the congruent tangent segments theorem, which is if two tangent segments to a circle share a common endpoint outside of the circle, then the two segments are congruent. Too much words? Some of you were able to understand and visualize it, but for most of us, it's a lot easier if we have a diagram for this particular theorem. So let's say we have a circle O, and from the circle O, we have tangent lines that share a single point outside of our circle. And what is that illustration? So this is our two tangent lines. We have line AB and line AC, and they share the same endpoint, which is point B. So in this particular theorem, we know that line segment AB has the same measurement as line segment BC. This is basically what this congruent tangent segment theorem is all about. So if we're going to write out the theorem in terms of this circle and tangent lines with ray AB and ray BC sharing the same point B in our circle O, we know that line segment AB is congruent to line segment BC, which means if line segment AB is equal to 10, line segment BC will also have 10 units as its measurement. So this is our second theorem, which we are going to be using so that we'll be able to solve problems similar to this one. So we are going to look for x, and the challenge here is to be able to formulate the equation that will help us find the value of x. And to be able to do that, we'll be using the theorem that we have learned from the previous slide, because if line AC and AB are tangent to a circle D, how are we going to find the value of x using this particular theorem? Well, we can, because we know that line segment AC is the same or congruent to line segment AB. And what is line segment AC? Line segment AC is x squared, which is equal to the values of line segment AB, which is 10x minus 9. And from here, we can now solve for the values of x, because all we need to do is to equate this to 0. So we subtract 10x and add 9 on both sides, which will leave us with x squared minus 10x plus 9 equal to 0. And by factoring, we know that we have factors of 9 that will give us negative 10 when you add them up, and that will be negative 9 and negative 1, because negative 9 times positive 1, negative 9 times negative 1 is positive 9, and negative 9 plus negative 1 is negative 10. So that means this quadratic equation can be modified into x minus 9 times x minus 1 equal to 0. And using the zero product property, we can equate x minus 9 to 0 and x minus 1 equal to 0. So we can solve for x, which is equal to 9, and x is equal to 1. So that means we have two values of x in our quadratic equation, which means we have two possible values for this particular illustration, and we're going to find that out from this slide. So now that we know that AC is congruent to AB, using this principle, we can equate x squared and 10x minus 9. And by setting it to 0, we have a quadratic equation that is factorable. And by factoring, we're able to separate 9 or negative 9 and negative 1. And by zero product property, we have x minus 9 equal to 0 and x minus 1 is equal to 0. Therefore, the values of x would be 9 or 1. And let's test it with the first value of x, which is 9. So let's say x is equal to 9. The value of line segment AC, which is the same as the line segment CA, can be found by substitution. So let's use line segment AC, which is equal to 10x minus 9. And if we plug in 9, we'll have 10 times 9 minus 9, which is 90 minus 9. So that means line segment AB is 81 units. And now that we have line segment AB, let's check it with line segment AC when x is equal to 9. So that needs to be the same as line segment AB, and it is because x squared, given that x is equal to 9, is 81. So that means our calculation is correct for x is equal to 9, but is it also true for x is equal to 1? Let's find out by plugging in x is equal to 1 to 10x minus 9 and x squared. And we know that 10 times 1 is 10 minus 9 is equal to 1, and 1 squared is also equal to 1. That means our values can also be true for x is equal to 1 using our solution. So this is how we use our values for x once we're able to figure out the equation that will help us solve for our problem similar to this one. So let's test our knowledge of this theorem and also algebra to find the measurement of the length of our triangle, also known as the perimeter, given that we have a circle inscribed in our triangle ABC. And we know that by just looking at our triangle, we know that we can form tangent lines that share the same endpoint, which means we can use this to be able to find the perimeter of our triangle using the theorem. And to illustrate that, we know that AD is equal to AF because AD and AF share the same point or endpoint outside of our circle that is tangent to circle O. So that means AD and AF will be both 10 centimeters. So this is going to be 10 centimeters for AD and AF, and we're going to use the same principle for BD and BE and for CF and CE. So for the second pairing, we have BD should be equal to BE because of the tangent line that we have here that shares the same endpoint as B. So that means if DB is 15 centimeters, BE is also 15 centimeters. And for CF and CE, which happens to share the same point for our tangent line, we can also say that they are congruent, which means if CF is equal to 8 centimeters, CE is also equal to 8 centimeters. And now that we have all our values for our line segments, we are now ready to find the perimeter of our triangle, because by adding up all the segments that's no longer missing or unknown, we'll be able to figure out its perimeter. So for line segment AB, which connects line AD and line segment DB, we'll add them up, which is equal to 10 plus 15. And for the second side of our triangle, we have line segment BC, which connects CE and BE. And we're going to have those values because we know that BE is equal to 15 centimeters. And we also know that CE is 8 centimeters. And for the last line segment for our triangle, we have line segment AC, which connects CF and FA. And we know that the value of CF is 8 centimeters and the value of FA is equal to 10 centimeters. And by plugging it all in and adding them all up, our perimeter for triangle ABC is equal to 66 centimeters. So this is why it's important that we know our theorems, especially in geometry, to be able to formulate the equation that will help us solve for the values of x. And for your Numberbender challenge for today, let's see if you can find the value or the measurements of line segment PQ and PR, knowing what you know now from our lesson for today. So, in geometry, it's easy if we know our words and technical terms and how it relates to our shapes. And sometimes it can be challenging if we need to formulate our equation so that we can solve for the values of x. Knowing what you know now, through practice, you'll be able to gain more confidence in answering complex geometry problems similar to this one, and hopefully you'll be able to practice more from our videos in our channel. This is Dr. E, and see you again next time. Bye!